Hello again. This is Math 2-115 coming to you from the College of DuPage. The title of this lecture is Encryption Applications, and as always, be an attentive learner as you watch this video. By way of introduction, number theory plays a key role in cryptography. The subject of transforming information so that it cannot be easily recovered without special knowledge. Number theory was the basis for many of the classical ciphers, first used thousands of years ago, and was in fact still used extensively until the 20th century. Those ciphers decrypt and encrypt messages by changing each letter to a different letter, or a block of letters to a different block of letters. We'll discuss some of the classical ciphers, including shift ciphers, as well as affine ciphers. These classical ciphers we will discuss are examples of what we call private key ciphers, where knowing how to encrypt allows someone to also decrypt the message. With a private key cipher, two parties who wish to communicate in secret must share a secret key. The classical ciphers we will discuss are also vulnerable to analysis, which seeks to recover encrypted information without access to the secret information used. These are code breakers, and we'll talk about at least one way to perform such analysis on shift ciphers. Number theory is also important in more modern encryption called public key cryptography, a type of encryption invented in the 1970s. In this, knowing how to encrypt does not always tell someone how to decrypt. And when you think about that, that's very subtle, and in fact, for a while, people didn't know if this would be possible or not. The most widely known public key system, called RSA encryption system, encrypts messages using modular exponentiation, where the modulus is the product of two very large primes. Knowing how to encrypt requires someone to know the modulus and an exponent. It does not require that the two primes be known. As far as is known, knowing how to decrypt requires someone how to invert the encryption process, which can only be done in a practical amount of time when someone knows what the two large primes are. And factoring things into large primes is difficult. This subject also includes the subject of protocols which exchange messages carried out to achieve a specific security goal, and we'll discuss two important protocols in this chapter. One allows two people to share a common secret key, and the other can be used to send signed messages, signed as in affixing your signature, so the recipient can be sure that they were sent by the purported sender. One of the earliest uses of cryptography was used by Julius Caesar, and this is called the Caesar cipher. And so what happens is he made these secret by shifting letters. And so for example, you could say, well, just shift 3 letters forward in the alphabet. And they could change this shift level every day. And they would do a wraparound whenever you went off the end of the alphabet. So for instance, if we were using 3-letter shift, the letter B is sent to the letter E, and the letter X is sent to the letter A. And this is an example of encryption that makes the message itself secret. Okay, to describe this mathematically, then what you can do is you say f of p, and p stands for the plain text, is equal to p plus 3 mod 26. And the mod 26 brings it back to a numerical representation. And of course, you had to assign letters to people, numbers, excuse me, to the letters. So A could be 0, B could be 1, and so on and so forth. Or you could use 1 through 26. Actually, you're better off using 0 there, but you get this. And so this is a way of encryption. Okay, so what does the secret message produce? From this message, meet you in the park, using the Caesar cipher, and this is the one. And you should really do these things, so let's pause and let's see how you did. Okay, so you replace the letters in the message itself with numbers, and that gives you this. Okay, so M is the 12th number in the alphabet, and T is the 19th number in the alphabet, and so on and so forth. Then replace each of these by f of p equal p plus 3 mod 26. Now, and so here you see that Since Y is the 24th letter, it gets transmit when you shift by 3, you go back to 1. So we wrap around, and if you do all of this transition, I encourage you to do it, because I could ask you a question like this later. You get this as the encrypted message. So to recover the original message from the secret message, you just use the inverse, and the inverse is p minus 3 mod 26, and that's called decryption. And you could use a different shifting thing. This would be K. And shifters are, and this is the inverse, and such are called just a shift cipher. And cipher is what you call the encrypted material, and so that is a shift cipher. And here the integer K is called the key, because you have to know that to know how the shift was happening. Let's illustrate this shift cipher in a couple of examples. So here's a problem that you should do. So you should encrypt this message, stop global warming, using the shift cipher with the key equal K equal 11. Please do this. And let's see how you did. So you should have translated stop global warming into this encrypted phrase. And this does go on to the next line. Warming had to be split over 2 lines here. Let's look at another example. Decrypt the cybertext here. Now this is encrypted, and here the key was 7. So now we're employing the inverse. You know what to do. Let's see how you did. What we do is we take each of those, change them into numbers, and then we shift them by minus 7 modulo 26, and we get these, and then we change it back, and this is translated into, again, experience as a great teacher. Now you can generalize this shift cipher slightly to slightly enhance the security by using not just a shift, and then here would be a shift of B, but also multiplying by A. Now since this is kind of like saying Y equals mx plus B, this is called an affine transformation, and the resulting cipher is called an affine cipher. So you have to know A and B to decode it. Okay, so here's an example for you to do. What letter replaces K when the function f of p is 7p plus 3 mod 26 is used for encryption? You know what to do. Let's see how you did. And you should note that 10 represents K, and so that means that f of 10 is, this is going to be 73, and 73 mod 26 is 21, and 21 represents V, so K is replaced by V. So now we're going to show how to decrypt messages using a affine cipher. So suppose this is the ciphertext is equal to this, and the greatest common divisor of A and 26 is 1. And by the way, you do have to have this relationship in order for this to work. To decrypt, we need to show how to express P in terms of C. So what we do is we apply the encrypting congruence that C is congruent to AP plus B mod 26 and solve it for P. And to do this, we first subtract B from both sides to obtain this. And because the greatest common divisor is this, we know that there is an inverse A bar, so we can multiply both sides by A bar to give us this. And because A bar is congruent to 1 mod 26, we have solved this, and that determines P. And P belongs to Z 26, and this is the thing that we have aligned with the letters of the alphabet. The process of recovering plain text from the ciphertext, that's the original message from the encoded message, is known as cryptanalysis or code breaking. And it can be a difficult process, but we'll talk about how to break messages that were encrypted using a shift cipher. But this is without knowing what is the shift. So the process of recovering this, so suppose we know that's produced by enciphering message using a shift cipher. Well, what really is known is the relative frequency of the most common letters in the English text R E is most frequent and way most frequent. T is next. A is 8%, and so on and so forth. So to do some analysis, we could look and we could say, what was the most frequently occurring letter in the ciphertext in frequency order? And we can say, suppose the first one is E. And then we can determine if, in fact, it is, and that allows us to solve for K. What is the shift? If the message produced by shifting the ciphertext makes sense, we assume it's correct. If it does not make sense, we consider the hypothesis of the most common thing by encrypting C, and so on. And it's a little bit of trial and error, but we continue our process until we have broken the code. And mathematicians make the best code breakers, and their work in World War II is known to have changed the course of the war. And there are even some movies about the imitation game is an example of the work of Turing there, and that's actually a pretty good movie to watch. Okay, so here's an example. Suppose we intercepted this message, and we know it was a shift cipher. What was the original plaintext message? You know what to do. Let's see how you did. Okay, so we start looking at it and we can say, well, the most common letter, and you have to, spend some time doing that, but the most common letter in that is K. So we hypothesize that the shift cipher sent the plaintext letter E is to K. So if that's true, then we can say that 10, which is K, is equal to 4 plus K. E was 4. Mod 26, so K is 6. So if we use K to be 6 and invert that, we get the early bird gets the worm. And because this message makes sense, we assume that the hypothesis K equals 6 is correct. Now, there's another type cipher, and by the way, you can use these in combination, one with another, but we're just talking about them as distinct techniques. It's called block ciphers. So shift ciphers and affine ciphers proceed by replacing each letter of the alphabet by another letter. Because of this, they're called character or monoalphabetic ciphers. Encryption methods of this kind are vulnerable to attacks based on analysis of the letter, as we've shown. So instead, one of the things we can do is we can deploy what is called a block cipher. And what happens here is you replace blocks of letters with other blocks of letters instead of replacing individual characters with individual characters. Such ciphers are called block ciphers. And so we'll look at a type of block cipher that's called a transposition cipher. And so what we do is we start with a permutation. We make a permutation of 1 to up to n. So we take a block that is m long, and we shuffle these numbers up with a permutation, which is a rearrangement of these numbers. They're all there, and then we shuffle the numbers. So that means to encrypt a message, we first split its letter into blocks, each of size m. And if it's not actually divisible by m, you add some random letters at the end to fill out the final block. Then you encrypt the blocks, P1 through PM, and so you get cybertext C1 through CM, and you get these blocks which have been shuffled. So to decrypt this, we transpose its letters using the inverse of the permutation, the inverse of sigma. And we'll look at an example of this. Okay, so we're going to use a transposition cipher based on the permutation of these, and we're going to shift 1 goes to 3, 2 goes to 1, 3 goes to 4, and 4 goes to 2. So that's how we shuffle them. So encrypt the plain text pirate attack, and also the second one is decrypt. This is encoded. And this was encrypted using this this cipher. So here you're encoding, here you're decoding. You know what to do. Let's see how you did. Okay, first you split them into blocks of each of 4 letters. So we get this is the encryption. This is the blocks of 4 letters. Okay. And that's pirate attack, but then we're encrypting this, so we send the first letter to the 3rd position, the 2nd to the 1st, and so on. So when you encrypt it, you get this as the block encryption. Now in part B, we're using the same thing, so the inverse of that goes backwards. It sends 1 to 2, 2 to 4, 3 to 1, and 4 to 3. So we apply that to these, and we get this is the plain text of this thing, and it's use water hose. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all, and see you as we continue this encryption lecture.